Hi everyone, welcome back. In this video, I want to make a demo video, a demo tutorial on how to use HFSS and MATLAB to generate FMCW SAR data. In the past, I've made a tutorial on how to generate step frequency SAR data using HFSS and then process that using back projection in MATLAB. So I recommend you can watch that if you want to use step frequency radars. But I thought it'll be nice to make another one on FMCW, how to generate FMCW SAR data, and then use that to generate images. So without further delay, let's get started. So you'll have to open HFSS, create a new project. So when you open HFSS for the first time, this is what it should look like. So what we'll say is insert HFSS design. And now I want to import a target, let's say. So maybe before that, let's just call this SAR demo. Okay. Before we import a target, let's do some basic housekeeping. We want to use SBR plus, shooting and bouncing rays. This is a geometrical optics solver in HFSS. And I also want to create a coordinate system. So I'll say Z target, which I'll set to 300 millimeters. So this is about, I'm just saying the target is 300 millimeters away. So you select this coordinate system. I'll call this target CS. And in this coordinate system, I want to import my model. So I've imported this. I mean, you couldn't see the selection, but I selected it. Selected a model that I had saved in my computer. So this is pretty simple. It's it's 5 corner reflectors, square corner reflectors, trihedral corner reflectors, they're called. It has a specific geometry. You can find it online and make it yourself, or you can use any target of your choice. So in this case, just for demonstration's sake, I'm using this. Select all of them, assign boundary, and perfect E. So perfect E boundary condition makes it basically a metal, perfect electric conductor. And you can set the roughness and things like that. But for simplicity's sake, I'm just going to set that to be 0. Okay, so now you have these corner reflectors as metals, and you can see it's symmetric about this origin in some sense. Okay, go back to the global coordinate system. And in the previous video, I actually showed how you can make your own horn antenna and then use that as a source to excite these targets. But in this case, just for simplicity's sake, I'll use a pre-made antenna instead. So the way you can do that is you can select an antenna option from here. Before we do that, what I would like to do is create another coordinate system for the antenna location. So I'll say X position, set that to 0 millimeters, Y position, 0 millimeters. Okay. So I'll call this TXRX coordinate system. So you select this, and then you create a parametric beam. This is the simplest form of antenna that you can use. It's essentially just you set the beam parameters and the polarization and the footprint size, and that'll give you synthetic antenna of some kind. Okay. I'll set that to 2 millimeters because that's typically lambda over 2 at 80 gigahertz or so. And that's where we'll be operating. I go to next, and then I say finish. And this beam by default is generated along X. So we want to rotate it to face along Z. So what I'll do is I'll select the beam. Right click, edit, arrange, rotate, and then minus 90 degrees. No, that should rotate about the y-axis. There we go. Okay, so now it looks like the beam is facing our target, which is nice. And I selected the beam width to be over 60 degrees. You can set that to be whatever you like, or based on the size of the target, and things like that, you can decide the beam width. But 60 degrees is plenty. Okay, so let's see what happens when I change the positions. If I make this 10 millimeters, it moves. Now it moves in Y, which is very nice. Okay, and automatically when you create the antenna, it creates an excitation. And one thing you need to do is right click there and then turn it on. So that will turn on this antenna. Okay, so that's about setting up the antenna itself. The next thing we want to do is to set up the analysis. So to do that, you right click analysis and you say add solution setup, and then you should get this pop-up window. I will select range Doppler, and I only want to use I channel. IQ will generate complex FMCW data, but in this case, we'll just deal with the real case. That's more typical. And you want to use chirp sequence FMCW. We actually need a time variable, which I forgot about. So let's do that. So I'll double click on any of these and I want to add a variable. I'll just call it time var. And then I'll say units of time. And then we'll make it seconds, set it to 0. And then say OK. And then go back and then say add solution setup again. Range Doppler. And see, now it automatically selects that as a time variable, which is nice. And here I'm setting some parameters. I'll explain what they are later. But if you know FMCW, if you watch the FMCW video, these should all be pretty straightforward. So I'm going to set the range resolution to be 18.75 millimeters. The range period to be 22.5 meters. Velocity actually doesn't matter in this case, since we are assuming that, it's the target is fixed and the radar takes each measurement at a fixed location. We're using basically a stop and go approximation. Okay. And the reason I chose these parameters is that I have an experimental setup right now, which has exactly these parameters. And in the future, I'll show you some results from that experiment as well. So it's just easier to start with this. So essentially the radar bandwidth is 8 gigahertz. The center frequency is 80 gigahertz. Chirp duration is about 48 microseconds. The A to D sampling rate is 50 megahertz. The frequency ramp rate is about 166 megahertz per microsecond. So this is the chirp rate. And the number of samples per chirp is about 2400, which is the chirp duration times the sampling rate. Yeah, and the pulse repetition frequency is around 5 kilohertz. These are for the velocity part, which we don't care about in this simulation. Okay. So once you have these set up, you can also change the ray density and the number of bounces. We can leave it as default for such a simple target. But for more complicated targets, maybe you want to increase this. Okay, and just hit OK, and that's it. So I think it's pretty much ready. We can say validate and then analyze. So this should just take a few seconds because it's geometrical optics. While that's being done, we can actually set up the results as well. So I'll say results, create range Doppler report, rectangular color map plot, and just set this as defaults and then say new report. Okay, I think it's done now. All right. So we look at the report now. Not sure why this is like this. Let's do it again. New report. Okay, nice. So you see that in the Doppler velocity, it's close to 0. And in range, which is along the y-axis, it's around 0.3 meters, right? Because this is up to 22.5 meters. But what we want to do is we want to export just the range data. We don't care about the Doppler data. So to do that, what I will do is I'll say create range Doppler data table. You can set this to be the same. We'll use a flat window. We don't want any windowing for simplicity, because in the theoretical developments that I made earlier in the previous videos, I did not use any windowing. And then we want to make the primary sweep range over all of them. And we only want one Doppler component, which is the zero Doppler. Okay. Go back to trace, and we want the real part. So we want the complex response plus the imaginary part. Okay. So I think that's pretty much right. And then we say new and close. Okay, so this generates the data table, and you can see that actually it kind of peaks at the 17th value, which is at 0.3 meters. This, yeah, you can see that it's kind of large here, and everywhere else it's close to zero, right? And then it goes basically zero after that. Okay. All right. So that shows how you can generate one data set. And now we use the same trick that I showed in the previous SAR video, which is this one, is you can use scripting to generate all of your data. So let's do that. So I'll say tools, record script to file, and let me create a new folder here. Called YouTube demo. And then here I want to create a script. Once you create a script, now any action that I take will be written in the script. So let me set the position to 10 millimeters, and then I'll set the Y position also to 10 millimeters. And then I'll say simulate, validate, close, analyze. So let me pause and come back once it's done. Okay, simulation is done. Took like a couple of minutes basically. And then what we want to do is right click here and then say export. And what I'll do is I will export it to, let me just export it here, but I'll change the name. So I'll say SAR data exposition in millimeters, Y position 10 millimeters .csv. Okay, save. And then I'll clear this. And then usually I actually clean up the solutions after each iteration, because when I run a large SAR data set, I don't want it to save all of that data for each iteration, each position, since I've already saved the actual data I care about. I don't want the simulation to save the results. Okay, and that's the end of the script. So I'll say stop script recording, and that would be done. And now what I'll do is I will open MATLAB, or you can open any, let's not use MATLAB, let's use, so, okay, maybe I'll use just Notepad. So that's my script, right? Now what I want to do is I need to use for loops to make sure that, I can collect data over a 2D grid, right? Okay, so I've already done it before, so I'll just replace what, I'll just show you what I've done. So I replace all of this with this. So what am I doing here? I'm saying, okay, for exposition in range minus 52, 52. I mean, the way for loops work in Python, I guess it doesn't use the last value. So this really goes from minus 50 all the way to 50, the step size of 2 millimeters. Same for Y position, goes from minus 50 to 50, step size of 2 millimeters. All of this is the same, except I've also changed this one. Earlier, this was 10 millimeters. Now it's, whatever the value of X position is, and whatever the value of Y position is plus millimeters. And I have also changed one more thing here, which is I've added a folder data in this location demo trial -data -this. You can set whichever folder you like. And also the name of the file needs to be changed, right? So for each different location, the name changes so that you have a set of all the files for different locations and the data is saved. Okay, so this is the script. You just update the script, save it, close this. Now, if I go back, this one, and now all I need to do is go to tools and then say run script. And then I can run the script. If I run the script now, basically it'll go through all of those positions and then save all of that data down, right? Maybe I can just show you what it looks like. There we go. So if I look at it from this perspective, we see that it's in the first position, -50, -50, and then it'll be -50, -48, -50, -46, and so on, and saves the data for this entire grid. I already done this, so I don't want to do this again. So I'll just say abort. Okay, now that's aborted. I have opened up MATLAB and I have a code here, which I'll run through. And I'm just showing you here that after running just one iteration at 0, it generated this file. Yeah, in this folder data. Right, so let's see what that file looks like. Before I do that, let me just run through the code of how I set this up. So I just start with CLC clear path, whatever. And now I'm setting up the radar operational parameters. So the bandwidth is 8 gigahertz, center frequency is 80 gigahertz. That's frequency in radians, speed of light. This is the beam width. I actually don't use it, so it doesn't matter. Again, the bandwidth, this is the range resolution, which is we saw was C over 2 times the bandwidth. And then the fast time domain parameters, which we set in the simulation. Sampling rate of 50 megahertz, time duration of each chirp is 48 microseconds. Number of samples is the product of these two, which should be 2400. The chirp rate in radians per second. And then this is the duration of the samples. So each sample is about 1 over fs, right? If fs is the sampling rate. This is the total pulse duration. Of course, the number of samples times each sample's duration. And then we create the time array, right? So this is the domain of the time variable, which we showed, I guess we used TP from -TP02 to TP02. This again goes back to the first FMCW video I had made. And range goes from 0 to a range resolution times n-1 with a step size of the range resolution. Okay, and then slow time domain parameters are the synthetic array parameters. So the spacing between each element position is 2 millimeters, which is about lambda over 2 or so. We'll discuss what exactly this needs to be in a future video, but just keep in mind a good rule of thumb is lambda over 2. And then for -50 millimeters to 50 millimeters in both X and Y, so that's a 2D array. And I'm just saying the Z position is 0. That's the length of the different X and Y parameters. And this is the total number of measurements we made in the slow time domain. Okay, data acquisition. So I'm assuming here that you have this folder data in which all of the, M number of files exist. Since here I only have one at 0, 0, I'm just showing you that, but I've already done this separately for all of the files. But let's just do it for this one. Okay, so what I'm doing here is, okay, X position 26, Y position is, in reality, it would be this, X position from 1 to XP, Y position from 1 to XP. And then you go through the entire data and then create a data matrix, which is the size mx by my by n over 2. Why n over 2? Because HFSS, since I used a real signal, only the I channel, it drops the second half of the data, the second half of the range data because it's redundant. I'll show you what I mean by that. Anyways, so this is your 3D matrix in X, Y, and time domain. So if you go back actually to the lecture notes, where is it? Yeah, this one. So we said that the measurement of the beat signal happens over X prime, Y prime, and K, where K was KT, which is a time domain variable. And that's exactly what we have here. Okay. All right. So you go in, you see what X pause and Y pause is, and you read the data, convert it to a complex variable, and then I'm plotting it in this case. So let's just, since we only have it for 1 point, I'll just plot it and we'll see what that looks like. Okay, so that's what it looks like, which makes sense. At about 0.3, which is where we place the targets, all 5 targets, we have a spike. Since all of them are very close in the same, almost the same range bin, you don't see all 5 of them separately. They all show up in the same range bin. That's okay. That's the whole point of SAR, is that you can now separate them. Okay, and I've used a lot of points because in the measurements I'm using so many, but you don't actually have to use so many. You can just use maybe, you know, one fifth or 1/4 of the number of points that I've used here. But since the target is so close by, but in general, in the measurement, I used a lot of points because there was actually a wall at some distance. So you want to make sure that that wall, the reflections from the wall don't get aliased onto your target. And that's why it's generally a good rule to have to use a higher number of points, sampling points. Okay. So basically you go through this. And then what I'm doing here is that I'm actually converting the range data that HFSS gives you back to time domain. The reason I'm doing this is because in reality, when you do an experiment, you will measure in the time domain, you sample the time domain signal. And we want to actually do our processing directly in the time domain because that would be much faster. But HFSS obviously gives you in frequency domain, so you want to go back to time domain and keep the data in time domain. That's what I'm doing here. So the first thing I do is I augment the data so that now I also have the negative frequency components, which is what I'm doing here. So let me actually run that. And then if I plot this, is this right? Should be 26, 26. Okay. Okay, so if I plot this, I should see this, which is now showing the 2 components, right? And HFSS basically cuts it in half, and you only see this part. But we also want this to reconstruct the cosine, right? You need the negative frequencies as well, which is what this is. Okay. Yeah, so once I have the fully reconstructed frequency or range domain data, I convert it back to time domain using an inverse Fourier transform. Right, so essentially, this is what you measure, and this is exactly equal to this SB that we have here, because here K actually was in time domain. Hopefully that's clear. I mean, if you watch this video and you understand FMCW well now, this should be pretty straightforward. All right. So what I've done earlier is I've actually done all of this and I saved it in this um, in this variable. So what I'll do now is I'll just load this. Maybe I've changed the names. This is all right. So let me actually clear everything. And I will just load this. Okay. So now you see I've loaded a 51 by 51 by 2400 data set. And what you want to do is reconstruct the image from that, right? And I'll implement exactly this equation now. Triple summation over SB times the steering matrix, right? Pretty simple. That's back projection essentially, and that's what I'm doing here. So I say, okay, X range is the same as the sampling points. You can change this, you can make this arbitrary, but in this case, I'm just making them equal. You can form your image at in any domain at any points you like. F tilde is what I'm calling the reconstructed image. I form a 2D matrix, and I form a 3D matrix of the time signal so that you can vectorize this summation, right? So essentially, I mean, this summation, not this, sorry. This is 3 summations over a 2D plane on which I'm forming the image. So that's 5 summations. I've reduced those 5 summations into 2 summations over for loops and 3 summations over a 3D matrix, which is a vector. Okay, so X goes from 1 to the length of X range. That's X, that's Y, and that's the R minus R prime, modulus R minus R prime. I make that also 3D. And then I implement the steering matrix, multiply that with the data matrix, and then I do the triple summation. And that gives me a single pixel, what the value is, and I do it over all pixels over these 2 for loops, and that gives me the total matrix. So I also ran this. You can run it. You can see that it's not very fast. For each pixel, it takes maybe a few seconds, at least on my computer. So what I'll do for now is I'll stop this. And I already saved this state before, which I renamed. Okay. So let me actually load that state. All right, so this is the state. So once you run everything up to here, this is exactly what you should have. Right, and now I want to form the image. So all I do is I make the 2D grid from X range and Y range, and then I plot the absolute value over the maximum value to normalize it. So let's see what that looks like. And that's what that should look like. So you see exactly the 4 targets that we had here. We bring this to 0, 0. Right, there we go. Right, so these are the targets. And we see that the positions, for example, this is at plus, 20 or 2 centimeters away from the origin, and this is 2 centimeters away in X, 2 centimeters, 2 centimeters, and that's at the origin in the XY plane. And if we look at this, it's again exact, and this is in centimeters, the X and Y axis. So this is 2, -2, 2, and -2. So that's it. That gives you the reconstruction. Okay, and let's see how long it actually took to compute. So that took about 3 minutes or so, 173.99 seconds. And this array is actually not that big, right? It is about 51 by 51. So in the experiments that I've done, the array size is a lot bigger. It's more like 251 by 251. If I divide that by 51 times 51, so that's 24 times longer for a single XY plane, right? If I use an array that's 251 by 251, and I create an image in a single XY plane, it would take me 24.22 times the computation time. Sorry, compute time, I suppose. Which let's divide that by 3600. So that's about 1 hour. It would take me about 1 hour, a bit more, in fact, because here this vectorization also takes longer. This step. It would take about, my experience, about 3 hours for a single XY plane. Now, if I want to do that in 3D, So I need to do that over 1200 um, range bins. That will be 1200 times 3 hours, which is 150 days. And that's crazy, right? You can't spend 150 days just to get an image. So instead, what I'll show is that you can reconstruct. In a future video, we'll use a different algorithm. So the conclusion here is that back projection is very slow for 3D imaging. That's high resolution, right? It takes 150 days to generate the image. What's the point? But what I will show is that you can make this much, much, much faster. So we'll see that if you want to create an image over 251 by 251 by 1200 points, you can do that in about 30 seconds or so instead of 150 days using range migration techniques. So that's for a future video. So let's move on and do a little bit more and see how we can generate data in other ways rather than using just HFSS. So what if I want to generate a large data set? Is there an easier way? There is. It's not as accurate as HFSS, but you can even do it synthetically because we do have the forward model, right? Which is, let me close that. So, we generated this forward model, right? This one. So we set for an FMCW signal, if a point target is a certain location, this is what the measured signal should be. That's sort of called the forward model. So you can use, in fact, directly the forward model itself. And that's what I've done here. So again, it's the same parameters and everything, and I'm generating some synthetic data. So I say, okay, I have these points located at these locations, same locations as an HFSS. And then I generate the forward model using this equation. So it's essentially just for each target, I generate what this function should be, what this signal should be, right? It's cosine times this term. I've ignored here the residual video phase term, which is this part. It's not important for short range. We'll discuss in a future video what to do if that exists. And I've also ignored another thing here, is I've ignored the support for short range targets. So what that means is that if your target is very far away, you actually don't get the signal in the time domain all the way from minus TP over 2 to TP over 2, right? Because there is some time delay for the signal to come back. So part of the chirp doesn't exist. I've ignored that effect because it's very close to because in this example, it's very close. But if it's not, then you have to add another window function here that makes the time sample time sample 0 for all the cases where the signal has not come back yet. But okay, for now, let's just use the simple model. So if you use this synthetic data generation model, let's see what happens. And then the rest of it is exactly the same. So once I have that data, I reconstruct using exactly the same equations. Right, so here I'm using EXP. Okay. So one thing to note actually is that I'm using exponential here in the steering matrix, even though here I'm using a real cosine, and that's fine because you can write a cosine as expansion of two exponentials. Essentially, your image is only valid for the first half. The second half, you get a copy of the image essentially. So it's okay to do this. All right. So I already ran this as well. So let me load that state. So this is the 5 target synthetic state. And then if you plot this image, this is what this looks like. Right, again, you have the 5 targets, and they should be pretty straightforward that this is what it should look like because this is exactly synthetic data. It's not from HFSS. Okay, cool. So one last demonstration I wanted to do is that let's say you have, an image, actual image. This is like an optical image that I downloaded of a gun. So now let's say I want to see, okay, what would the radar image of this look like before actually doing any experiments, putting this in HFSS as a 3D model, and then generating all that data just to get an idea. What's the simple way to do this? So a simple way to do this is to generate a point cloud of this image and then use that point cloud to form synthetic data. So that's what I'm doing here. So I read this image and then I convert it to binary scale, zeros and ones. And then I rescale the image to be the dimensions that I want it to be in real size. And then I randomize the order of points. And the reason I do that is because I'm only using a few of the points and not all of them. So you randomize all of the order of the points, and then you select a subsample of the points because you don't want all of them. And then essentially just use that as the X and Y position of all your scattering phase centers, right? So just to give you an example, let me run this code. I should have it here as well. Okay. It's the same code. Okay, so if I run this, this is what I get, right? It's a point cloud of the gun image. Now, if I did not do this and I ran this, then this is what I would get. It's very dense, the number of points. And I don't want that. I don't need actually that. I have, 200,000 points for X and Y basically. So instead, I just used a few of them. You can make this as small as you want, really. It's just a matter of computation time. Okay, so let me run that again. So that's what that looks like. So it's just, you can treat these to be like some kind of scattering phase centers. And the distribution is not even, but still gives you a good idea of what the radar image might look like. Okay. So now that you have these positions, you can save them using this. And you go back to your synthetic data generation. And then now what you do is you run the same thing again. And here, instead of this, I am going to do this. So I load those X and Y positions. And then I use those points as my point scatterers, right? And since I'm summing over all point scatterers, I generate synthetic data over all of them. So again, you can run this, which I've already done and saved. So I'll just load that state. Okay, so now let's look at what the radar image looks like for this. And that's what it looks like. Right, so this should look similar to one second. Okay, so that's figure 1. And then that's this as well. Okay, that's what we have. So you see that, okay, you can kind of see this hole. You can't really see the trigger very well because the resolution is not that good. And here, in fact, I've scaled the gun down just so I can make it faster in terms of simulation time. But yeah, that's what this is. So hopefully that helps. I mean, you can definitely tell this is kind of a gun. And you can generate images of different kinds of targets and things like that. Okay, I think that's pretty much it. So it's somewhat of a relatively shorter video. And this hopefully gives you an idea of how you can use HFSS to generate synthetic data for FMCW SAR. It's the same for MIMO really, so I don't want to make this too long. Essentially for MIMO, what you would do is you would have a separate transmitter and receiver, and then you go to excitation, you select TXRX, and then you would turn on just the cross components. And then you can move them separately using 2 separate variables, generate the data set, and then use the same reconstruction algorithm that we talked about to generate that data and to reconstruct the image. So I'll let you play around with the MIMO part. That's pretty straightforward once you understand this. So hopefully that was helpful. If you have any questions, leave them in the comments or you can send me an email. Thank you so much and have a nice day.